In this lesson, we're going to take a look at continuity on a closed interval. So let's first recall our definition for continuity. For a function to be continuous at a number x equaling c, we require that the limit as x approaches c of f of x equals f of c exists. Now remember, this is the short version of the continuity definition, where we have rolled all three conditions into one statement. Okay, so we're just using the short version of continuity here. Now let's consider the graph of a function like this. So here we have a function, the square root of 4 minus x squared. Now its graph looks like this. Okay, it's just the upper half of a circle of radius 2. Okay, remember, if we write y equals the square root of 4 minus x squared, well then y has to be positive because there's a plus out here. It's not written, but it's implied that this is a positive number. And if we square it, we get y squared equals 4 minus x squared. Bring the x squared over, x squared plus y squared equals 4. But we do require y is greater than 0. And this is a circle of radius 2, but it's the upper half because we require that y is greater than 0. And so this is what our graph looks like. All right. Now let's take note of one thing here. It looks like our graph is continuous from -2 to +2, right? Because I can start here and I can go all around this curve without picking up my marker here, and so it looks fine. There's no problem. There's no breaks in this graph. It will satisfy this definition up here everywhere, but there's a little problem with our definition at -2 and +2. So let's note what that definition is, and then we'll fix our definition. So here's the issue. We notice that f of 2 is 0, right? If I put 2 in here for x, if I put 2 right here for x, I get the square root of 4 minus 4. There's nothing wrong with taking the square root of 0. Right? Square root of 0 is 0. And also the same for -2. If I put -2 in here for x, I get back 0. Now they're defined, and it looks like our function should be continuous on that interval from -2 to 2, and including -2 and 2, so the closed interval. However, our continuity definition doesn't quite work at x equaling 2, since we cannot state that the full limit as x approaches 2 of f of x equals f of 2, which in this case is 0, because f of x is not defined on both sides of 2. You see, this full limit statement means x approaches 2 from the right and from the left. Now, we have no problem with x approaching 2 from the left, but if x is approaching 2 from the right, that means x is a number bigger than 2, like, say, 3. But if I try to put 3 in here, I get the square root of 4 minus 9. That's a negative number, and we don't want to deal with taking the square root of negative numbers here. We're only considering real valued functions. So this function we're going to consider it to be undefined from 2 to positive infinity. So there's a problem with letting, in this statement down here, letting x approach 2 from the right. So how do we fix it? Well, the way we fix it is we just ignore the right hand part, and we say we're only going to consider the limit as x approaches 2 from the left. That's all we do. So looking down here, we can say that f of x approaches f of 2, or 0, as x approaches 2 from the left. There's no problem there. If I plug a number in a little smaller than 2 in here, that's no problem. So we can say that the limit as x approaches 2 from the left of f of x is f of 2. And then we say f of x is continuous at x equaling 2. So in other words, at the end point, at the right-hand endpoint of the interval from -2 to 2 at the right-hand endpoint here, we're only considering a left-hand limit. All right, and the same thing over here at -2, except we only consider a right-hand limit. So we say, and we note that f of x converges to 0, which is f of -2, as x approaches to -2 from the right. So we can write limit as x approaches -2 from the right of f of x equals f of -2. And we then say f of x is continuous at -2 because this condition is satisfied. So in other words, at the end points of our interval of interest, we only consider right and left hand limits and not full limits. That's all. Pretty easy. So here's a definition. So we say a function is continuous on a closed interval, a,b, if it is continuous on the open interval first, and then the right-hand limit as x approaches a of f of x must equal f of a, and that must exist. It must be a number. And the left-hand limit as x approaches b of f of x equals f of b, and that exists. It is a number. All right, so that's our definition for continuity on a closed interval. We just have to use the right and left hand limit definitions because the function may not be defined on both sides of a or both sides of b. All right, so let's take a look at an example. So what we want to do here is find the interval over which the square root of -x squared plus 2x plus 3 is continuous. So what we have to do is just find where -x squared plus 2x plus 3 is greater than or equal to 0. All right, so notice that this polynomial factors as follows. And now setting this equal to 0, we see that the solutions are going to be -1 and 3. All right, so what we're going to do now is use a sign pattern technique with these numbers and find where that polynomial is positive. So now we're of course going to pick test values like -2, 0, and 4. Plug these numbers into the polynomial here and see if we get back positive or negative values. All right, so if we plug -2 in here, notice we could also plug -2 over here, and what we would get is a negative times a negative times a negative. That's going to be a negative number. So this function is negative from -infinity to -1 just by putting -2 in here for x, or in here. Now if you put 0 in here, you're going to get negative times a positive times a negative, right? Negative times positive times negative. That's going to be a positive number. So we are going to be positive from -1 to 3. All right, that's the interval we're looking for. If we put 4 in here just to check, we're going to get negative times positive times positive. That's going to be negative. All right, negative times positive times positive. And over here we were negative, negative, negative. All right, so therefore we see that the polynomial is positive from -1 to 3, and that is going to be our interval over which this function is continuous, -1 to 3, with closed brackets. Now that's our answer. And that's all we have to do. But let's actually just verify using the definitions that we just looked at, let's just verify that the function really is continuous over this interval. So now what we're going to do is we're going to say, let's pick a value c between 3 and -1. And now let's verify that the function is first continuous on -1 to 3 with open interval, an open interval like this. So I'm going to pick c in here. Then let's notice the limit. Now what we can do is just put c in for x by properties of limits. And that's equal to, alright, so that shows that the function is continuous over the open interval from -1 to 3. Also keeping in mind that this term underneath the square root here, this is positive, because that's what we determined up here. Alright, so I know f of c exists, and the limit is f of c, so that shows continuity on the open interval. Now what about at the endpoints? Well, at -1, we need to consider the limit. So we're taking a look at the limit from the right as x approaches -1. Now notice we can just put the -1 in here for the x, and we get the square root of 0, which is 0, of course. All right. Notice if we put -1 in for x, this polynomial is 0 by what we found up here, with -1 being a root. Right. And this is equal to f of -1, of course. If I go back to the original function, put -1 in for x, we get 0. Alright, so this shows that the function is continuous at -1 at the interval where we have a closed bracket. Now if we look at the limit as x converges to 3 from the left, we do the same thing. Of course, we get the square root of 0, because 3 is a root of this polynomial, as we found above. That is 0, and that is also f of 3. Alright. So now, both of these combined here, all three of these, then show that the function So all three of them show that f of x is continuous on the interval from -1 to 3 with closed brackets, because of what we've done here with the right-hand limit and the left-hand limit. Alright, so that concludes this example. Let's take a look at a quick little graph of what this function looks like, just to verify that we've what we found here. So here's the graph of the function. Right here is -1, and here is 3. And yes, it does look like we can graph the function. It's nice and smooth. We don't have to pick up our pencil. And it does indeed look like it is continuous from -1 to 3, including -1 and 3. Alright, so that does it for our discussion of continuity on closed intervals.